Okay, so last time we basically discussed the second order tensors. So basically, as said, the second order tensors are a map from one vector to another vector. So if I apply this tensor on this vector, it would give me another vector u. And the interesting fact about tensor is that it's a second order mapping. Obviously, like it takes something a vector and it basically spits out another vector, but it is a linear mapping, and a linear mapping basically implies that there is a lot of stuff going on in here. So basically a linear mapping, as like we said in linear algebra, so like if I apply this on v1 plus a times v1 plus v2 vector, that would give me a v1 vector plus a v2 vector. So basically these are two different vectors. If I sum over them and apply, like basically if I sum the vectors individually and then apply the linear transformation, it would be same as applying the linear transformation of on both of them and then summing them. And this is the first rule for linear transformation. And the second rule for linear transformation is that if I multiply any constant by that vector c1, like c times v1, then it would be the same as multiplying c times the transform vector, that is av1. Like after transforming the vector av1, it would like if I multiply the c, that would give me the same vector as a times cv1. And if I were to basically individually represent both of these properties combined in a combined way, that I would basically write that a times alpha v1 plus beta v2 would give me alpha times a v1 plus beta times a v2. Like basically it's both of them sum and the product one together. So basically it should be linear with addition, and it should also be a scalar multiplication. A tensor has it's basically the same as matrix, which we done in MA 106. So yeah. Now in the next slide, basically now we need a way to represent it. Like we have done this in our MA courses, so still I can basically just go over this. So basically a second order tensor is something. Just a second. Basically a second order tensor is something which satisfies this. Yep. A second order tensor is basically a tensor which, like, if I were to basically systematically represent a tensor for which we can actually represent in a matrix format, I can basically do one thing. I can basically know where my unit or my basis vectors, which I have considered, are being transformed by this linear transformation. So, like, suppose I have this new basis. I define this new basis. Like if I have this, if I apply my basic transformation a tensor on my first basis, it basically goes to some new basis that I can basically write as e1 dash, and this other basis e2 would also go to the e2 dash, and e3 would also go to the e3 dash. So like these are my new bases after transformation. And like let's suppose I say that e1 this is it. Let's suppose I say that e1 is alpha times e1. Like I can represent e1 as like in our original basis. So like e1 would be in some direction, an arbitrary direction after transforming a with e1. So e1 dash would be alpha times e1. E1 dash would be beta alpha times e1 plus beta times e2 plus gamma times e3. So basically, it's some vector represented in terms of the original basis which I have written here. And there are some like e2 is also represented in that way. E3 is also represented in that way. So I can basically write that alpha, beta, and gamma in terms of matrix. Like I have this matrix of linear transform, right? I mean, I have this a is equal to something, some column. I can write basically alpha as a11, alpha like beta I can write as a12, and gamma I can write as a13. And obviously you can basically know that because I would have this, right? I mean, I have a11, I have I mean, basically, I have a11, I have basically a21, and I have basically a31. So basically, alpha, beta, and gamma, I can basically write as this one column of this matrix A. And if I have like similarly, I can write e2 dash as like some alpha dash e1 cap plus beta dash e2 cap. So basically, I can also write this as a like basically as a12. I can basically write this as a22, and I can basically write this as a23. So like basically this alpha, beta, gamma are mapped to a column, and the E2 vector is also mapped to a column. So basically they are all mapped to a column as such in this case. So yeah, basically once they are like, I mean, I can say that if they are mapped to a column, I can basically write this identity that ej cap is equals to aij times ai cap. So like if I have like I can basically know, right? I mean, this is a11 times e1 cap, this is a21 times e2 cap, and this is also a31 times e3 cap, right? So basically you can see that one, and here like there's this two here, and there's this also two here. So basically ej dash cap is equals to ai times ei cap, I mean aij times ei cap. So basically this is what basically how basically we are defining a tensor. So this is an index notation how we basically represent a tensor on like how it transforms the unit basis vectors to this new basis vectors. So now basically I can define some additional operators on it. Like I can basically what I can do is just I can like I need to find this like how are basically our aij defined, right? So what I'm doing is I know that this satisfies this, like ej dash is obviously a operating on ej. So what I'm doing is I can take a em, I can multiply it as with like our original em vector. So em times dot em I'm dotting with a times ej cap, right? There's this a like ej dash, this is obviously ej dash. So what I'm doing is basically I'm dotting em dot em with ej dash. So I'm writing ej dash as aej. So this is right here. So what I'm getting is em times aij times ei. Like I had this, right, aij times ei. So I'm basically writing a dot a operating on ej cap is equals to aij ei. And like after some calculation here, right, like I can write this like aij is obviously a constant. So I'm basically taking it out, and like em dot ei are basically in the same basis vector. So like em dot ei I can write this as delta ij. So yeah, here it is delta mi, right? Just hmm, yeah. So basically em dot like I mean em dot aaj is basically amj. So basically I have this a delta mi, I can write I is equals to m. So basically I can write I can replace I with m, and this is amj. So amj is basically this amj, like the component of like amj of this tensor would basically be equivalent to dotting the em vector, like the em vector of the original basis with the ej dash vector, the new basis. Like ej dash is basically this, like the ej vector after being transformed by linear operator. Like if I'm applying the matrix a on the ej cap, then I get ej dash, and em dot ej dash would basically give me this amg. So like like I can also basically write this, any element is a is a component of em in vector ej dash, or like or aej. So like basically this is some revision of like MA106. You can basically check the proofs of this in MA. Like we have done this in our linear algebra course. So you can just basically go through this as such. Hmm. So basically now that I know what each component means, like I have A, M, G, and like I have all these other things and all this crazy stuff, and I know what basically they represent. So like how if I want to represent them in matrix, in a matrix format, how do I represent that? So basically I define a format that there is this thing called matrix that there shouldn't be a transpose here. So like if I were to represent A as a matrix, I would represent it by A11 component to be here, A21 component. Note that this is the A21 component here, and A12 component is right here. This is not, this is basically the opposite convention of what we did in MA106. But like this is basically how we define a like a matrix, or a like the matrix representation of a tensor. Like A is a tensor, right? So basically if we want to represent in a form of matrix, I can write the A21 component of it here. So basically A21 component is the same as what the A21 component means in MA106, but it's just that we are writing the A21 component in this manner. In like we're just basically, if we were to write a matrix of all the values of a tensor A, we are just basically replacing A12, A12 which used to be here in MA106. We are just instead of A12 instead of writing A12 value here, we are just basically writing it right here. Like we are writing A12 here. So there's no difference in basically indices. Like A12 in MA106 is equals to A12 right here in this course, but it's just like when we are writing A12, A23, and all the components of that tensor, basically we are just basically using this notation to write the matrix representation of a tensor. So basically, there's only difference in the matrix representation of this tensor, but there's no any basic difference in the like the tensor in the indexes or like the components of this tensor. Like I mean, MA1 in MA106, which our linear algebra course, we said that A11 would be equals to the same A11 which we are referring to in this course. So basically everything is the same. It's just only that we are representing in a different notation for this matrix in this matrix notation. So yes, that is basically like how we like define this matrix. So like if obviously like as I said, like if we were to do it for like basis vectors, then we can also do it for any random vector, right? So I can basically, as we said, that this was always the case that we would consider that a u vector is after being like if I apply this matrix on like the distance array on this vector v, then I would get another vector u. So basically I can write this as v, I can write this as vj ej, and basically I can write this as vj aj ej. And so like basically we can apply we can take this vj as a constant outside, and we can apply a vector on each of these ej's, right? So like each of our original each of our original bases would be transformed to this ej dash, right? Basically in this case each of our original vector are transformed in this ej dash, and like obviously our new vector u would be like some would be also be some linear combination. So like our u would be um times em, which means basically ui ei plus u1 e1 plus u2 e2 and so on basically. So basically this is UMEM, and this is also VJ EJ dash cap. So basically we have this EJ dash cap, right? So after like basically it's a painstaking derivation. So I can like basically I can just basically go over. So basically in the end, what we want to remember is how are we basically applying, like how are basically this two things related. Like I mean, if I have this components of UI, then how can I like if I have this components of vector v, then how can I get our components of vector u, which is after I apply the linear transformation, or like I mean the if I apply the linear transformation a on v. So basically it's the same as like the ith component of u is equals to vj times aij. So basically you can just that there is this the dummy index is obviously the j index, and the free index is I index. So basically vj and aj, so basically you'll have to sum over. So basically u1 you can write as v1 a11 plus v2 a12 plus v3 a13. So basically since you wrote this j is occurring twice, so you will basically sum over the j, and this is like what you get basically. And obviously when like you like we can also basically do this in terms of matrix multiplication, as like which is shown here. So like matrix in matrix multiplication also we know the the matrix multiplication rules right here. So yeah, this is like the matrix multiplication how we used to did in our MA 106 course. So yeah, so basically this is the matrix multiplication. So this is a11 a12, and like we used to multiply this column with this row. So basically it's the same, like v1 a11 times v2 a12 plus v3 times a13, and like it's the same as this. But like just note that here like everything we did is the same as like the MA106 course, but this is only one thing. Like I mean our matrix representation of the tensor array was not this. I mean, in our matrix representation of tensor array, we had a21 here. So basically, when we are applying like when we are applying this a is equals to uj, so we are basically when like if we are considering the matrix of this tensor array, so we know that this tensor array is obviously a11. Like I have written it right here. So this is a11, a21, a31. So basically when we are considering the matrix, we just basically take the transpose of it. So basically a12, a13 are basically in this, I mean in these columns, and then we basically we can apply the same matrix multiplication as we did in MA106. So basically if we go with index notation, everything is the same and everything is considered consistent. But only if when we are considering like if you want to do matrix multiplication, then obviously you'll have to write the matrix and then you'll have to multiply it the rows with its column. So basically when you write the matrix form of this tensor, you'll just have to take the transpose of it. Like I mean the matrix form of this tensor, so you write a1 to a21 and all this so on. So this is not basically the correct way to do it. So you cannot then apply the matrix multiplication from this, you need to keep a12 in this column. So this a12 and a13 should be, here should be a12 and here should be a13. So basically you can just take the transpose of in this case. So basically, I know this is kind of counterintuitive than what we did in MA106, but once you like get your head around this, it's quite easy to grasp. So like this was basically everything we had on our second order tensor. So after that, basically proving some identities is quite easy. I'll just basically go through it. So we can have the product of two tensors too. Like if there are two tensors a and b, then their product would be ab times v. I can take a vector v. So I can take ab times v is equals to a times the bv vector. So like I can basically apply first the transformation b on v vector. I would get another vector, and on that vector I would apply the transformation a. So basically that's how we do a product of two vectors. And basically after a like the derivation, which is right here, you can just basically look over through it. So basically after like we did the derivation, it's the same as matrix multiplication. Like matrix multiplication of two matrices, it's the same as that the I and jth component of the ab tensor, like the product tensor, would be equals to aim times bmj. So in this, just know that there is AIM and there is also BMJ. So basically here the M index is repeating, right? So M index is twice. So basically you'll have to sum over the M index. So you would write AI1, like you would have to write AI1 times B1M plus AI2 times B2M and so on. So basically you'll have to sum over that index, but it's like basically it's the same as how you did matrix multiplication. So like AB times, you write the matrix A and you write the matrix B, and like it's the same as that. It's as simple as that. So basically you can just basically do the matrix multiplication when you need the product. So and in index notation you can basically do this. So like you know the index notation, and it's like very quite simple. And as we know that there's also this transpose of this tensor. So basically the transpose of it, this tensor, as like it's the same as linear algebra. So if I can take, so a transpose the ij component of a transpose is equals to aij, like a transpose gi is equals to aij, and it's the same as like what we did in linear algebra. And like this is now the basic stuff of about like matrices and tensors. So like we know that what's the determinant of tensor. So like determinant of a tensor is basically equal to the determinant of the matrix, and like that is the scalar. And there's also this inverse of a tensor, and there's also this concept called symmetric tensor and asymmetric skew symmetric tensor. And it's basically the same. Like you have this matrix representation of the tensor, and you are just basically checking if it's symmetric or if it has an inverse or if it has a determinant, and so on and so forth. Now there's this important thing called a skew dual vector. And basically a skew dual, for like a skew anti for a skew symmetric matrix, you can basically write a dual vector for that. For like I mean, if I have this skew symmetric matrix, then like these components, like these omega y, omega z, and omega x, I can basically compile them into a vector. So basically it has a very nice property that if I apply this matrix on any vector b, then this vector, it's basically equal to this. Like if I omega y, omega z, and omega x, omega y, and omega z cross it will just basically land on this dual vector times cross product times v vector. So basically it's a simple property, and like it's basically a concept which like you can basically write a dual vector of any skew symmetric matrix, which is obviously perpendicular to b, and which is obviously also perpendicular to the dual vector. And as like basically as it's a cross product, it will obviously be perpendicular to both of them. And like this is just a concept about the dual vector. And this is also a thing called a tensor product or dyadic product. So basically a tensor product between two vectors, like if I have two vectors a and b, and their tensor product would basically, if I have this like a and b, two vectors, then this basically this symbol does denote a tensor which is formed from these two vectors a and b. So if I apply this tensor on this vector, then it maps it to b dot c times a vector. So it's also basically a formula which you have to remember. Like this tensor product has this property, and this is how our tensor defined. So basically, it maps C to a scaled version of A, and that scaled version is basically B times C vector, the dot product. And like this is basically the property of like it's a tensor product, and it is also like this tensor product is basically also you can write this as like I and jth tensor product would be equals to ai bj. So like obviously you would have this tensor, so like it would be a11, then it would be a2 b1, and then it would be a3 b1, and so on, basically so on and so forth. Basically if you know the ij component, you can basically write this as ai bj of that tensor. So I guess yes, that would be. And yes, there's this basic stuff of orthogonal tensors. Like orthogonal tensors are basically the tensors for which C transpose is equals to C. Like if we have an orthogonal tensor, so basically the orthogonal tensor is basically a tensor which preserves the length of the vector. So like if you have a certain length of a vector, like if you have a vector v, so if you apply the orthogonal tensor to it, it will map to a vector with the same length. Also preserves the angle between two vectors. So like if you have two vectors at an angle theta, and after transformation, you'll also like again the two transform vector would also have the angle theta. So basically, it's just the property or like how the orthogonal tensors are defined. So basically, a property about orthogonal tensors is that their inverse is equal to their transpose for that. Yeah. And like basically this is all just like derivations about this. So basically what we like in this, basically these are coordinate transformations which we can basically go over through your linear algebra. So basically what we can do is like I'll just tell you the result for this case. So basically if you have a vector like you have two coordinates, right? There are two coordinates, and like there are these are your original coordinates. You have your original coordinates v1 v2 and v3, and you have your transform coordinate. Like there is some new set of coordinates e1 dash, e2 dash, and e3 dash, such that like from if you want to go from e1 dash, e2 dash to e3 dash, you would have to apply the transformation matrix q, like the transformation matrix q which we learned in linear algebra. So it's just basically that you have this vector v, and you'll have to do that. I'll not annotate in this case. So basically, yes, if you have this, so basically you'll have to this v is equals to q times v dash. So basically, you're basically comparing the components. So you have a vector fixed in phase. So you have this vector defined as v1 e1 plus v2 e2 plus v3 e3, and you want to know what it's basically how it is defined in the other bases like v1 dash, v2 dash, and v3 dash. So basically, what you can do is basically you can apply this transformation matrix, and you can multiply it with the v vector. So in that case it's like very simple. So there's also this rotation of 2D rotation. So we know that there's this vector v, there's this vector v in this case. Yep, there's this vector v in this case, and it is like basically we have two components for it. There's this v1 dash component along e1 dash, and there's this v2 dash component along e2 dash, and this is also v1 component along e1 and v2 component along e2. So basically what we can do is we can write v1 dash and v2 dash as q11, q21, q12, and q22, which is basically equals to q transpose of it, and this is v1 and v2. And basically these components you can basically find it by like from the rotation matrix, the cos theta, cos 90 minus theta, and all that, and like all that stuff has been like basically covered in the linear algebra course MA106. So like MA106 notes would be really helpful right now. And so basically it's just the same as the linear algebra. The linear algebra is all very basic and stuff. So in the end we just we have this orthogonal basis or this orthogonal tensor, and we can just basically apply this transformation to get this new tensors as such for this, to get the new coordinates. If we just basically do a coordinate switch, the same vector would be represented in different coordinates, and like v1 dash and v2 dash. And basically if we have v1 and v2, we can just apply this matrix transpose, q transpose, and we'll have this. So yeah, with that I guess we would end the tensor part for this. And like it's very simple. I guess a basic brush up of linear algebra would do the job, and like it's very simple, and I guess you would easily understand that. And I guess these are some results which I guess you can find that in the notes. So after this, like in the next video, we can start with the deformation of a solid body.